Welcome, and thank you for joining this webinar, From Connectivity to Sensing Revolution, How Wireless Can See the Invisible, prepared by Albert Research Team. Today, we're exploring how wireless sensing isn't just another buzzword, it's the fusion of communication networks with environmental awareness, turning everyday Wi-Fi routers and 5G towers into silent sentinels that detect motion, monitor health, and optimize cities without adding hardware. The specific technologies that make sense of these signals. Channel state information, CSI.
CSI is really foundational, especially for sensing using Wi-Fi and modern cellular networks like 4G and 5G. You can think of it as a highly detailed fingerprint of the wireless channel right now. It characterizes every single path that the wireless signal takes as it travels from the transmitter, TX, to the receiver, RX. It captures the combined effect of everything happening in the environment, the signal bouncing off walls, reflection bending around corners, diffraction scattering off furniture, people, all of it.
It's much more detailed than just looking at signal strength.
Simple signal strength, RSSI, is just one number representing the total received power. CSI gives you granular information about both the amplitude and the phase shift of the signal across multiple subcarriers. Modern systems like Wi-Fi and 5G use MIMO and OFDM, orthogonal frequency division multiplexing. OFDM is key here. It splits the wide communication channel into many narrow independent frequency bands called subcarriers. Each one of those subcarriers carries its own unique amplitude and phase information, reflecting how that specific frequency traveled through the environment. So instead of one RSSI number, you get 58 complex numbers, each with amplitude and phase. That's a lot more information about the channel.
When an object moves or even just exists in the channel, it causes multipath propagation. The signal reaches the receiver via multiple paths, some direct, some bouncing off walls, some bouncing off the object. Each path has a slightly different delay, different attenuation, maybe a phase shift. CSI captures these specific frequency selective changes across all those subcarriers.
So how does that level of granularity allow for something as subtle as monitoring breathing or heart rate, which involve tiny movements?
It allows us to analyze what's called the micro-Doppler shift. A person's chest moving due to breathing might only move, say, a millimeter or so. It's tiny. But this minuscule movement causes a very small cyclical frequency shift in the reflected radio waves due to the Doppler effect. CSI's fine-grained resolution across those subcarriers allows sophisticated algorithms, usually AI, to pick out this incredibly faint cyclical signature. It can differentiate the subtle pattern of breathing from, say, the larger, coarser movement signature of a person walking across the room. Without the high resolution provided by CSI, detecting those tiny, fine-grained physiological movements would be basically impossible with RF alone. And the really exciting short-term enabler here is that commodity CSI extraction, the ability to get this detailed data, is now being integrated natively into standard COTS Wi-Fi hardware, particularly with the new Wi-Fi 7 chipsets rolling out.
That's huge. It means we could potentially turn existing enterprise Wi-Fi networks, or even home networks eventually, into sophisticated monitoring systems, maybe just with a software or firmware upgrade. We generally define two primary sensing topologies based on where the transmitter and receiver are relative to each other. First, you have monostatic sensing. Think of this like the AP acting as its own little self-contained radar unit. The transmitter and the receiver are the same station, usually the AP itself. It sends out a signal pulse and then immediately listens for the reflected echo bouncing off objects in the environment. It's good for quick presence detection, maybe basic range finding. The second is bistatic sensing. This is more like traditional triangulation, or how radar often works. It uses separate, distinct transmitters and receivers. Often it actually leverages the existing communication links already happening in the network. Let's talk about passive Wi-Fi radar, or PWR.
Instead of needing a dedicated radar transmitter emitting signals specifically for sensing, PWR cleverly treats the ambient Wi-Fi or cellular signals, the signals that are already saturating the air for communication purposes, as the source of illumination. The receiving device then effectively acts like a passive radar system, just listening to the echoes of these ambient signals. In a traditional monostatic radar, the transmitter and receiver are co-located. They're in the same box. In PWR, they are inherently separate. The Wi-Fi access point over there is the transmitter, and your sensing device over here is the receiver. This bistatic geometry, having separated transmitter and receiver locations, allows for much better detection of objects that might be heavily obscured or located in areas where the direct signal path is weak. You're essentially analyzing reflections and signal changes from multiple angles simultaneously, leveraging the multipath rather than just being hindered by it.
That sounds like the recipe for building a system that can actually work reliably in a complex, cluttered environment like someone's apartment or a busy factory floor.
Joint CSIP-WR fusion, often combined with sophisticated AI, is how we address that critical technical challenge of multipath complexity. The goal is to ensure that whether the motion is direct line of sight or heavily obstructed behind furniture, the system can maintain high accuracy and reliability. How do wave, T-Hertz, and radar techniques achieve that high localization precision? They have issues with signals dying out quickly, right?
The signal strength drops off much more rapidly with distance compared to sub-6 GHz signals. To counteract this, wave and T-Hertz systems rely heavily on massive antenna arrays. These large arrays allow the system to perform sophisticated beamforming, concentrating the transmitted energy into very narrow, highly directional beams, sometimes called pencil beams. And the ultimate synthesis of all this seems to be ISAC integrated sensing and communication. Let's be really specific. How does ISAC differ fundamentally from just, say, putting some sensing antennas and communication antennas on the same cell tower? Isn't that just coexistence?
ISAC is not just coexistence. Coexistence simply means two separate systems might share the same physical infrastructure or maybe take turns using the same spectrum. ISAC implies a much deeper, more fundamental fusion. It's designed right down at the waveform and signal processing layers. It means the signal waveform itself is intrinsically dual use. The very same radio wave simultaneously carries data bits to a user and extracts information about the surrounding environment to send back to the network.
What are the engineering or system-level benefits of integrating sensing and communication that deeply?
The benefits actually feed back directly into improving the communication system itself. Firstly, ISAC offers better spectrum efficiency because the same radio resources are effectively serving two functions at once. Secondly, and perhaps more importantly, it can drastically improve the precision of techniques like beamforming. If the network has extremely accurate, real-time information about where a user is located, where potential obstacles are, maybe even the user's predicted movement, all derived from the sensing function, it can direct the communication beam much more accurately towards the user and steer it away from interference. This not only saves network energy by reducing wasted signal power, but it can also significantly boost data throughput and reliability for the user. It transforms the network from being largely reactive to being proactively managed based on a real-time understanding of the physical environment. The big strategic takeaway seems clear. We're really moving beyond just connectivity. We're turning signal interference, which used to be a nuisance, into valuable insight.
So what does this all mean? The message is clear. This wireless technology isn't just enhancing networks. It's enabling a sensing revolution that redefines interaction with the physical world. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.